All right, here to knock out the Unit 3 part of our study guide, filling in the blanks as we go. Just a quick little walkthrough of the Unit 3 material, properties of water. This is our heaviest chemistry-based unit, which is usually the hardest unit for everybody who takes marine science, and so I would spend some extra time with this one and make sure that you have at least a basic understanding of some of the key terms here. Starting at the top there, under properties of water for Unit 3, atoms can be found alone, such as atoms of helium, or they can bond to other atoms and form a molecule. Molecules are the result of two or more atoms that are chemically bonded. H2O is an example. That's our first blank there. Lots of other examples that we could have put there too, which is certainly not the only one. But H2O is our example that we use here. Water is also a compound because it has more than one element. Note like O2 is an example. It's a molecule because it's two atoms bonded together, but it is not a compound. It's just two oxygens. In order for it to be a compound, it has more than one element. So H2O, again, is an example. You have hydrogen there as well with the oxygen. Covalent bonds are when atoms share electrons versus an ionic bond where electrons are stolen. Oxygen has a negative charge. The hydrogens have a positive charge, meaning they have more protons. Each end of the molecule has a different charge. This makes it polar. Polarity is what gives water its great dissolving ability. We'll mention that again later, maybe not. We'll keep on going. Just polarity is where you've got an opposite charge at each end. That's what helps water be a great solvent. Cohesion, big term here. I can almost promise you there will be a question related to this on your final. Cohesion is water's ability to stick to itself. That's all you've got to understand. When water molecules stick to other molecules, that is cohesion. Adhesion, on the other hand, is water's a tendency to stick to other materials. The example that we used in class was the water molecule hanging off of the leaf. It is sticking to the leaf through the force of adhesion. That force is greater at the moment than the force of gravity trying to pull the water down to the ground. Water is extremely unusual in that it is less dense as a solid than as a liquid. So a floating layer of ice helps to insulate the water below it so that it does not freeze as well. 3.2 then, heat and density. Temperature reflects the average kinetic energy for particles. Heat is the total kinetic energy. Temperature is average, heat is total of all of the particles in that substance or object. So to kind of compare the two together then, a cup of hot coffee, compare that to the Atlantic Ocean. The cup of coffee has a higher temperature, right, because its average amount of energy is higher, but the ocean has much more heat, even though its temperature is going to be significantly lower. It has much more heat because there's so much mass to the ocean, so its total energy is more. Specific heat is the amount of energy required to raise a substance 1 degree Celsius. The amount of heat needed to raise a substance's temperature is referred to as its heat capacity. Be familiar with that term. I can almost assure you it will be there. Particularly this part. Water has one of the highest heat capacities of any naturally occurring substance. And so the ocean absorbs a lot of this heat. Because of water's high heat capacity, the ocean is able to absorb a lot of the heat in our atmosphere. It helps to moderate Earth's temperature. Density of liquid, of water, slowly increases as temperature drops. The density of water decreases. Let me try this again. The density of water it's getting more dense as the temperature drops until it hits 0 degrees Celsius. And then at that point, at that freezing point for water, that is when density rapidly decreases, which is what makes the ice then float to the top. So higher temperature is going to make something less dense, right? The particles are spreading apart, making it less dense. Higher salinity is going to make it more dense. Lots of things in the water, particles there, making it more dense, kind of thicker, if you will. Surface layer, also known as the mixed layer. This is the least dense. This is the layer of water at the top of the ocean. It is exposed to the atmosphere. That sunlight is a large part of what makes it the least dense. So that heat is spreading the particles apart. The pycnocline layer density increases. That density increases mostly due to depth. And then the pycnocline is what separates the surface from the deep. The deep layer then is the most dense layer. Usually it's below 1,000 meters, and this is 80% of the ocean by volume. Most of the ocean by volume is deep layer. Our thermocline, that's going to be a big one. They love throwing that term around for the test. Thermocline is the depth at which there is a rapid temperature change in the ocean. So temperature is staying relatively stable, and then at the thermocline, there's going to be an area where it rapidly decreases, particularly in tropical water. Pressure, light, and sound. I'll try to run through these quickly. This video is getting a little longer than what most of them have been. Turbidity is the measure of water clarity. So high turbidity equals low light. That's what we're looking for there, low light. The photic zone is the area in the ocean where light is present. Light never reaches greater than 1,000 meters, usually much, much less than 1,000 meters. The aphotic zone is where light is not present. Red is absorbed most quickly, and blue penetrates the deepest, which is typically why that's kind of the color that we see as we look out across the water, blue and green. Well, red is gone after about 30 feet. You can't see red any further after that. In the ocean, sound travels much further and faster than light. Pressure increases dramatically. I'm going to kind of go a little bit quicker now. Pressure increases dramatically with ocean depth. Moving on to the water chemistry piece, water also acts as a solvent. Here we go, back to that word now, which means that substances can dissolve in water. Rain washes down the land and dissolves substances in it, and that's referred to as runoff. That's how some of our salt and other minerals get into our ocean water, is through runoff. The salinity is the total amount of salt that's dissolved in the water. Seawater has an average salinity. It's about 3.5% salt. The saltier the water, the denser it is. Many gases are also dissolved in seawater, including oxygen, carbon dioxide, and nitrogen. The pH of the ocean is dropping, and the ocean is becoming less alkaline, becoming more acidic, and that's referred to as acidification. And about 30% of the CO2 emitted into the atmosphere each year is dissolved into the ocean. So not only is the atmosphere becoming inundated with CO2, but the ocean is now as well. And the organisms that are going to be most impacted by this are going to be things with shells. Yeah, there you have it. A little bit longer there to try to make the rest of them shorter, but there is Unit 3. Peace.